Hello everyone, welcome back to Power Electronics and Laboratory. Today we will study over three-phase rectifier, three-phase. So I'm not going to explain in detail, but I will briefly touch on the difference between three-phase rectifier and single-phase rectifier. And then also I will talk about the current commutation in three-phase rectifiers. So those 2 points will be the highlights of today's lecture. So till last lecture we studied single-phase rectifier. So we considered two different cases. One with current commutation interval, and the other one was without current commutation interval. And the consequence of current commutation interval were two points. The first one is improvement of THD. Improvement means actually the decrease of THD number. And then the second point is output voltage is decreased. So due to current commutation, the output impedance would subtract the voltage out of the reference voltage. So some people can say current commutation interval is a good thing in terms of the input AC side, but still is a negative effect in terms of the DC output side. Okay, so you may think about in both ways: good impact for the AC input side, and then bad impact for the DC output side. So a few weeks ago I introduced a very interesting tool, interactive power electronics tool. You can see in the slide. Please take a look at our screen. This is open software. It's publicly available in the website, or I also posted in my homepage, course homepage. So its name is Interactive Power Electronics Seminar, developed by the University of Engineering in Zurich. ETH. I think this stands for Erdgenosische Technische Hochschule in Zurich. This is a top engineering school in Switzerland. And this tool were developed by multiple national scholars. And we have one profound Korean professor, Professor Choi Jae-ho from CHONBUCK National University. So I deeply appreciate his help. So if you remember, I showed one interesting example about the DC-DC converter, but now let's take a look at the single-phase rectifier. Okay. So here, this is ohmic load, right? This is ohmic. This is ohmic load means the resistance. What was our type in our course note? We studied under current source, right? So, but this time this is resistance. So it's slightly different. When we have a motor drives connected in downstream, you know, when we're gonna learn inverter in next class, those inverter-driven motor load can be modeled as a current source. But most of the DC-DC converter is modeled by resistance here. Okay. So now this waveform here is input single phase source, this voltage source. Okay? The European folks represent voltage source like this. Okay? Please don't be confused. This stands for the voltage source, not current source. And this shows resistance. When it is shaded rectangle, then it means inductor, right? It's, I think European people seems to be more practical in terms of the circuit symbols. And this is, and everybody can tell what is this? Full wave rectified voltage at the output from here to here, right? And then this green waveform now stands for the input AC side current. The DC load current, right? DC load current, because this DC load current is DC output voltage divided by resistance. So it has similar wave shape as this DC output voltage. And this black one is now, what is this? What could it be? This is AC side current, right? So as compared to our example, AC side current was like the square waveform in our case, right? But in this case is very much sinusoidal, right? So I would guess the THD is very small, below maybe 1%, right? So if I operate this animation shows the path of the current flow, right? So when we are at this interval of positive voltage, then the current will flow through this diode and return to this bottom diode, right? Like this. And when it's crossed over to the negative side, then our current direction is reversed. So it flows like this, okay? Here. So it's repeating again when it's positive and negative, right? So what about the current commutation interval? In this case, current commutation interval is ideally 0, which means this changing happens instantly, so without any delay. So we cannot observe any current commutation phenomena. Why? Because we don't have inductance at the AC side. So this was made possible because of 0 inductance. Okay? So ohmic load is pretty simple. Now let's take a look at the other example. Here. So what is this? Now it's a little bit complicated. Okay, so now everybody can tell we have a shaded rectangle representing inductor, right? And what about this? We have a voltage source. Voltage source. So what kind of circuit element can be modeled by the voltage source? It is capacitor, right? Capacitor. So when we have a capacitor, and then usually we have at the downstream we have a DC-DC converter. So this voltage source is called DC link voltage. DC link. This side is called DC, right? DC. So I have told you several times that this rectifier is like a workhorse. Workhorse means the one used in many different ways. Okay, it's heavily used. Workhorse. 그죠? 일하는 말 굉장히 많이 사용된다는 뜻입니다. This is a workhorse in power electronics because we can rectify AC voltage into DC, right? Now, what kind of things we can do after this stage, downstream. We call this downstream. Downstream, upstream means up, and downstream means, the following stage. And if we have some current, this like AC side, DC, AC, and then we have connected to motor, right? Okay. And sometimes this can be modeled as current source, as we have investigated. Okay? It means it's quite inductive. But if we have a DC-DC converter, then we have a very strong DC-link voltage source here. So obviously now this is DC. We have some load. In this case now we can model as DC voltage load. Okay? And this capacitor is called DC Link Capacitor. What does it mean by link? Link is like, you're connecting two different things. So link means is connecting downstream DC-DC converter together with upstream rectifier through this DC link. Okay? We can also say AC link. We have an AC link too in power electronics. When something is connected through the AC, then we call it AC link. But this is DC link, and we have a capacitor at the DC link side. So this capacitor is called DC link. So the one now you are looking at the screen explains this typical situation. We have a DC link capacitor, and then probably at the downstream we have a DC-DC converter load connected. So it could be quite interesting to take a look at this. Now, since we have a voltage source, the waveform now seems quite tricky here. Okay, everybody can tell now this green one seems to be the input AC source, right? And this blue and the sky blue, this blue is the DC link current, okay? And this sky blue, and this pulsating is AC side current. So it's quite special that, there is some mode. Oh. It stopped, sorry. Okay. Here, even though this AC voltage now enters positive, the current doesn't flow. Why is that? Because at this stage, AC side voltage is not big enough to forward bias this diode and this diode. So it's still, all diodes are reverse biased. 즉, AC 볼티지가 여기서부터 이렇게 해서 이 시점까지는, 여기까지는, 이 두 다이오드가 다 역방향으로 걸려 있어요. 왜? 이쪽 전압이 더 높기 때문에. 그래서 이 시점에 딱 들어가야지만 지금 이게 뭡니까? 이게 지금 DC 볼테이지로 지금 이게 DC 볼테이지죠. 요게 이렇게 같아지는 시점에 여기까지가 이제 다이오드가 역방향이고 여기서부터 요 그린 전압이 요 빨간색보다 커지는 시점에서 다이오드가 도통이 되죠. 네? 당연하죠. 그러면 여기서부터 전류가 쭉 흐르는 거죠. 이렇게. 그 다음에 이렇게 이제 흐르다가 이렇게 오다가 다시 또 꺼지죠. 그 다음에 이쪽 역방향에서는 이 시점 이렇게 이 전압이 커질 때만 비로소 다이오드가 켜지게 됩니다. So that means we have a zero interval from here to here, right? Okay, and from here to here. So what kind of lessons can we learn from this? Okay, first, the most important factor is THD. What do you think about THD? Now this is AC side current, right? Is this good? Good means, is this sinusoidal without harmonics? Well, you can think that here the current is very much distorted. Okay? So it's in reach of harmonics. So, okay, we can say in terms of THD, this is pretty bad. And also, what about the power factor? What do you mean by power factor? Power factor is average power. The definition of power factor is average power divided by apparent power, right? This was the definition. But if we proceed some calculation now, power factor is composed of two products. One is displacement factor times what? We have one additional term which is called distortion factor, right? Distortion. So displacement factor is the angle, cosine of angle, which is the angle difference between the voltage and the fundamental of the current. Okay? And distortion factor representing the harmonics, right? Distortion. So distortion factor is somehow related with THD. 그죠? displacement factor는 전류의 기본파 성분과 전압의 위상차, 위상차 알파에 대한 코사인 값이고, distortion factor는 순수하게 하모닉이 얼만큼 있냐는 그거죠. 이거는 THD하고 관계식이 있다고 그랬죠. 예? distortion factor가 그겁니까? 저기 하모닉, 토탈 하모닉 분의 전체 전류인가요? 예. 자, 그러면 이 파형에서는 어떻게 될까요, 여러분? Right? So this waveform now is the AC side current. Okay? And you can tell that the fundamental of what do you think about fundamental of this? Maybe it looks like this, right? So it has some, angle difference. Angle difference. Power factor is now, cosine alpha is not the unity here. And also it has some distortion factor, less than 1 here. 그죠? 이게 기본파 성분을 잘 보면 이게 지금 전압 기본파 성분이고 전류에 대한 기본파 성분 여기 안 나왔지만 한 대략 한 이 정도 되겠죠? 뭐 이렇게 해가지고 좀. 네? 그래서 입력 전압하고 이렇게 위상차가 보이시죠? 그래서 코사인 알파가 여기서는 뭡니까? 1이 아닙니다. 저희가 다뤘던 여기가 인덕티브한 그 커런트 소스일 때는 정확하게 구형파였죠? 구형파의 기본파 성분은 전압하고 그때 어땠나요? 위상이 일치했었죠? 여기서는 이렇게 좀 틀어집니다. 즉, 파워 팩터가 1이 안 됩니다. 물론 구형파 같은 경우에는 디스토션 팩터가 굉장히 나빴지만 여기서도 나쁘죠. So what am I trying to say? I'm trying to say this power factor is worsened. And unfortunately, all the SMPS that we have in everyday lives can be modeled by this. Right? 저희가 지금 갖고 있는 컴퓨터, 핸드폰, 차저, 그다음에 TV, 그다음에 여러분이 생각할 수 있는 거의 모든 전자제품은 다 이렇게 모델할 수가 있어요. 네? 그래서 여러분이 아마 커런트 스코프로 이걸 딱 찍어보면 전류가 대부분 이렇게 나옵니다. 네? 자, 그러면 이게 뭐가 안 좋냐? 파워 팩터가 안 좋아요. 파워 팩터가. 그래서 이게 뭐 가랑비에 옷 젖는다고 아주 조그만 파워들이 파워 팩터가 나빠지면 뭐 별로 신경 뭐 한 수십 와트짜리 뭐 별로 아닐 것 같은데 그런 것들이 무지 많이 모여주면 어떻게 되죠? 엄청나게 파워 팩터가 나빠집니다. 네. 그래서 뭐 제가 항상 얘기하지만 인버터나 이런 모터 같은 경우는 부하가 크다고 그랬잖아요. 부하가 큰데 오히려 그러한 여러분들이 갖고 있는 TV나 이런 뭐 SMPS 컴퓨터 이런 것들이 더 파워 팩터가 안 좋아요. 그래서 그것들이 합쳐지면 양이 많기 때문에 그래서 이제 한국전력에서는 이게 파워 팩터 나빠지면 소비자들이 고생하는 건 아니죠. 예, 전력계통 회사에서 어페런트 파워를 많이 설치하기 위해서 더 많은 돈을 투자를 해야 된다고 말씀을 드렸는데 그래서 파워 팩터를 THD와 마찬가지로 그 1로 설계하게끔 유도를 합니다. 예? 그래서 파워 팩터 코렉션이라는 서킷을 앞에다가 이렇게 그 기능을 추가하는 경우가 있습니다. 파워 팩터 코렉션. Okay? So I think in your course book, reference book, you have a separate chapter about power factor correction. Let's take a look where we have. I'm sorry, this book I think doesn't have separate chapter about power factor correction. Anyway, this power factor correction is very much heavily used concept in industry. So I'm telling you this because you should be familiar with this term power factor correction. Power factor correction is a circuit which improves power factor by having some kind of switching technique at the AC side. And the reason is this power factor is pretty much low so that it has to be improved. Okay? 그러니까 요 회로에서 보시다시피 이렇게 입력 전류의 파형이 그 디스플레이스먼트 팩터하고 디스토션 팩터가 나쁘기 때문에 이런 것들을 개선하기 위해서 그 어떠한 그 스위칭 테크닉을 쓰는데 거기까지는 제가 뭐 여러분들 말씀을 드리진 않지만 파워 팩터를 개선시키는 회로도 있구나 그렇게만 알아두시면 되겠고 그 이유는 이러한 싱글 페이스에서 역률이 나쁘기 때문에 많이들 그러니까 고려가 되고 있는 점입니다. Okay, so let's take a look at the other example. By the way, here, so here you can take a look here. When the input AC voltage is now increasing over this DC link voltage. Now it starts to conduct. But then why it doesn't turn off at this point? 왜 여기서 꺼지지 않는 걸까요? 여기서부터는 그러니까 AC 전압이 이 빨간색 전압보다 즉 이 전압보다 커지는 시점에서 딱 ON이 됐는데 이렇게 그 다음에 왜 줄어드는 시점에서는 안 꺼지고 이만큼 더 갈까요? 자, 그거는 바로 이 인덕터에 흐르는 전류가 계속 흐르려고 하는 특징이 있기 때문에 그런 거죠. 즉, 이 인덕터에 걸리는 전압이 이 전압에 더해져 가지고 가해지기 때문에 약간 이렇게 늘어져서 더 턴온이 되는 겁니다. 네, 그래서 이게 여기에 딱 동기가 돼 가지고 꺼지지 않는 이유가 거기에 있는 거죠. Okay? And this time now we have an inductance at the DC link side. Okay? So situation would be slightly different, but the overall is same as before. Okay? Here. And you can play with this, DC voltage. Right? The current wave shape becomes a little bit tricky. And now this one is more a realistic case. Actually, I should have explained this earlier than this particular example. Now this is exactly the same as this. Okay? 이게 여러분들 실제로 지금 가장 많이 쓰이고 있는 SMPS의 그 모델이라고 보시면 되겠습니다. 이렇게. 왜 그렇죠? DC 볼티지는 없으니까요, 아이디얼하게. 그죠? 그래서 이게 DC link, we have a DC link capacitor and the ohmic load. And here, so. Now the waveform now becomes quite complicated. 여러분 간단한 것도 굉장히 복잡해지죠. 네, 그렇지만 그 프린시플은 똑같습니다. 자, 여기서 보시게 되면 now where is the AC side input voltage? Here, right? It's green one. It's AC side input voltage. Now the second most important thing is DC link voltage. Before, when we have a DC source, it was a flat. But since now we have a capacitor, it's no longer flat voltage. Instead, we have some ripple. This one is now capacitor voltage. 자, 그 전에 우리 회로에서는 이쪽을 어떻게 모델했나요? 그냥 스티프한 볼테이지 소스로 했죠. 그냥 볼테이지 소스. 근데 지금 같은 경우에는 이게 캐패시터로 모델이 됩니다. 그럼 아까 거하고 지금 거하고 차이가 뭐냐? 자, 캐패시터 값이 크면 클수록 여기에 걸리는 특성을 DC 볼테이지 소스라고 우리가 근사화할 수 있다고 그랬죠. 그래서 캐패시터는 전압, 그러니까 DC 소스, 그다음에 인덕터는 전류원, 커런트 소스라고 제가 누누이 얘기했죠. 그러면 이 캐패시터 값이 만약에 적어지게 되면 어떻게 되느냐? 적어지게 되면 그러면 이런 현상이 생기는 겁니다. 이 전압이 이렇게 거의 일정하지 않고 이게 이렇게 왔다 갔다 하는 거죠. 자, 캐패시터 전압이 왔다 갔다 하는 건 뭐예요? 충방전을 한다는 얘기죠. 충방전. 캐패시터 전압이 올라갈 때는 충전, 내려갈 때는 방전. 올라갈 때는 충전, 내려갈 때는 방전이죠. 그러면 이 충전할 때 보면 지금 충전 타임인데 여기 지금 충전이죠. 충전하고 여기 방전이죠. 예? 자, 방전할 때는 자, 이게 보시다시피 이렇게 부하 쪽으로 전류가 방전하죠. 그다가 다시 여기서 이렇게 또 충전하고 방전하고 충전하고 방전하고. 그죠? 자, 근데 충전할 때, 자, 방전할 때는 이렇게 간다는 거는 이해하겠죠. 근데 왜 이런 쪽으로는 방전 안 하죠? 왜? 다이오드가 길을 막고 있으니까. 오로지 방전은 이쪽으로만 할 수 있죠. 근데 충전할 때도 스틸 부하 쪽으로는 전류가 흐르죠. 이렇게. 그죠? 왜냐하면 이건 부하는 단순히 DC 전압에다가 딱 인가된 거니까 항상 전류는 흐르죠. 요 전압 나누기 저항에 의해 가지고 그만큼. 그러면 왜 이렇게 충방전이 생기느냐? 자, 충전 타이밍을 보게 되면 어쨌거나 이 다이오드들이 온이 돼야 돼요. 자, 다이오드가 온이 돼야 된다는 얘기는 다이오드들이 포워드 바이어스가 돼야 된다는 거죠. 순방향이. 자, 다이오드가 순방향이 된다는 얘기는 이쪽 전압이 여기보다 높고 이쪽 전압이 여기보다 낮다는 얘기예요. 즉, 요 두 개의 요 전압이 요 DC 링크 전압보다 클 경우에는 포워드 바이어스가 걸려서 이렇게 충전을 하고 전압이 작아지게 되면 이 다이오드들이 역방향에 걸려서 꺼지게 되죠. 그 시점이 바로 이 시점입니다. 자, 여기 지금 보시게 되면 이 DC 링크 전압하고 AC 전압하고 같아지는 포인트죠. 네? 이게 아까 죄송합니다. 아까 여기에서 보게 되면 요 DC 링크 전압이 지금은 플랫했죠. 이렇게. 이게 플랫했 이렇게. 바로 요 시점. 자, 요 시점에서 아까 턴온 된다고 그랬죠? 요 입력하고 DC 링크 전압이 맞아 떨어지는 부분에서 그거하고 요 맞아 떨어지는 시점. 네? 여기가 더 잘 보일까요? 여기. 요 AC 전압이랑 DC 링크 전압이랑 맞아 떨어지는 시점에서 온이 되는 거예요. 그죠? 그러다가 언제 오프가 되냐? 이쪽 전압이 여기보다 더 많이 충전되어 있을 경우에. 그죠? 즉, 여기까지 쭉 방전하다가 여기서부터는 같이 충전을 하죠. 네? 그래서 쭉 충전하다가 여기서부터는 이제 더 이상 충전이 안 되죠. 왜? AC 전압 값이 여기보다 더 떨어졌으니까. 네? 이렇게. 그죠? 자, 그러면 AC 입력 전류의 파형을 볼까요? AC 입력 전류는, 이거죠, 요거 파란색. 아마 지금 요거는 지금 그 시뮬레이션 상에 좀 오를 것 같은데 요 전류를 보시면 되겠습니다. 이렇게. 아까 전류에 비해서 어때요? 엄청나게 디스토션이 생겼죠? 이 전류가 여러분들이 실제로 예를 들면 컴퓨터 같은 걸 켜놓고 파형을 찍어보면 전류가 이렇게 나옵니다. 네? 이 전류의 파워 팩터는 어떨까요? 일단 디스토션 팩터도 안 좋을 것 같고 디스플레이스먼트 팩터도 안 좋죠. 그래서 저희가 항상 얘기한 대로 파워 팩터 코렉션 서킷이 필요하다는 얘기입니다. Okay, so I have shown you several, these conditions or circuits for the single-phase diode rectifiers. I suggest that you go back home and play with these tools. Have you ever played with this tool? 여러분 이거 해보신 적 있어요? 한 번이라도 해본 사람? 우리 전북대 학생들이 바빠서 아직도 못했는데 아무튼 여러분 저기 코र्स 홈페이지에 올라가 있죠? 이거 그냥 다운로드 받으셔가지고 설치해서 이렇게 한번 해보세요. 한번 해보시면 또 달라집니다 느낌이. 오케이. 그리고 저기 요 비디오 강의 들으시는 우리 인터넷으로 강의 들으시는 분들도 요 툴을 제가 올려놓을 테니까요. 한번 심심하실 때마다 한번 이렇게 해보시면 또 전력전자가 새롭게 느껴지실 겁니다. So, the title of today's lecture is Introduction to Switch-mode Inverter. So, starting from the original power electronic application, I have told you several times that the AC side motor is the most frequent type of the electric load. It covers almost more than half of whole consumption of electric power, right? So motor is very much ubiquitous type of the electric load. Okay, motor is everywhere, like compressor in inverter and refrigerator and vacuum and mixer and drill. So motor is quite a popular type of electric load. And in order to drive motor, we need AC voltage, right? AC voltage, because AC motor is more popular than DC motor. In fact, we need a DC to operate DC motor, but in case of AC motor, we need AC voltage, okay? Then, early 19th, when we don't have inverter, what kind of solution did we have? 1950s or 1960s. We directly hooked AC motor to AC, three-phase AC input, right? Almost till 70s or 80s, right? 20th century, we used direct connection of AC motor to AC input. Why? Because these were not available those days, right? Then the obvious disadvantage is that this AC side voltage, amplitude and frequency are fixed. Amplitude is, as you know, 220 volt and frequency is fixed, 60 hertz. So which means we don't have any tools to control the motor. In order to control the motor, we have to vary the amplitude of voltage and also the frequency, because you know the rotating field frequency is synchronous with input side frequency, right? So what kind of control technique did we have to manipulate the process? The answer was we use mechanical or hydraulic controls. So process means like ventilation and heat exchanging or etc. 그러니까 즉 모터를 이용해서 우리가 그 어떤 공정을 제어할 때는 바로 이 모터하고 AC 볼테이지를 바로 연결하게 되면 주파수하고 전압이 고정되어 있기 때문에 제어가 안 되죠. 제어가 안 된다는 얘기는 모터의 회전수하고 토크 이런 것들을 제어할 수가 없다는 얘기죠. 그러면 어떻게 제어를 했었느냐? 정기적으로는 안 하고 기계적으로 했다는 얘기죠. 기계적으로. 어떻게? 밸브를 조정하거나 우리 여기 여러분 옆에 있는 그 레디에이터에 보면 이렇게 밸브 있죠? 예, 그 밸브. 그렇게 밸브를 열고 닫고 조절하거나 아니면 댐퍼 같은 걸로 해가지고 조절을 하고 했는데 그거는 결국은 어땠죠? 효율이 굉장히 낮아요. 효율이. Right? So think about this. The efficiency of the most popular type of load means something, right? The motor covers, how much have I told you? More than a half of whole consumption. And if I talk about efficiency of the most common type of load, that's quite important. 그러니까 모터가 그렇게 많이 쓰이기 때문에 이런 모터 드라이브의 효율성은 더 중요한 거죠. 더 중요한 거. So now people start to think about the inverter solution, switch-mode inverter, right? So this inverter now converts from DC to AC. And then this AC voltage is now very much flexible. Flexible means it can have a variable voltage and variable frequency. So we no longer need any type of mechanical or hydraulic control tools. Like we don't need the valve or we don't need any kind of damper. Do you have a valve in refrigerator? No, you just press the button and then it will control the speed of the compressor. So this switch mode inverter now has brought like a revolutionary improvement for the motor drive system. So it was developed early 70s or 80s using transistor technology. Now, in order to use switch mode inverter, now we definitely need to have a DC source, right? Because this is DC to AC inverter. So we need to somehow generate DC, and as you have learned last few weeks, we have a converter called rectifier, and this diode rectifier performs the conversion from AC to DC. And why are we using diode? Because this is the most cheapest solution. Cheap, right? Cheap. But since this is not controllable switch, this output DC voltage is fixed, right? Do you remember? VD is fixed, and VD somehow decreased with respect to output DC current during commutation interval, right? 그죠? VD 값은 고정돼 있죠. 다이오드인 경우에. 그러니까 이게 싸우기도 하지만 VD가 uncontrollable하다는 단점이 있습니다. 그리고 이제 우리 Commutation property 배웠을 때 요 ID 전류가 증가할수록 어땠나요? VD가 이렇게 감소했었죠? 아웃풋 임피던스 때문에. 그 굉장히 중요한 공식이에요, 여러분. 예. Okay, so and this type of inverter now is the most frequent type of the motor drive system that you can ever find these days. I think this is the most popular example these days. And since 10 years ago, we now start introduce so-called switch-mode converter, right? Now people have seen that this DC-link voltage should be controllable. So we now replace this diode rectifier with so-called switch-mode converter. Okay, switch mode converter. This is called switch mode converter, and this functions exactly the same as the rectifier, except that now it can control the DC link voltage, and this converts from AC to DC. I think I have once explained the meaning of inverter and converter. Sometimes people are confused with these two words. Actually, inversion, what does inverter mean? Inversion literally means reversing, right? Reversing. 그죠? inversion이라는 얘기는 직역하면 바꾸는 거죠. 바꾸는 거. So rectifier means changing from AC to DC, right? rectifier 뜻에 보면 뭘 곧게 하다는 뜻이 있죠. 자, 그럴 때 옛날에는 rectifier 반대 개념이기 때문에 인버터라고 했습니다. 인버터. 네? 그럼 컨버터는 뭐냐? 컨버터는 컨버전의 명사형이죠. 그러니까 그 뭡니까? 컨버전 한다는 거죠. 컨버전이 뭐죠? 변환시킨다는 거죠. 그러니까 어떻게 보면 컨버터 안에 인버터도 포함이 되는 거죠. 네? 왜냐하면 인버터도 DC를 AC로 컨버전 하는 거기 때문에 그 어떻게 보면 컨버터가 더 광의의 그 뜻을 갖고 있지만 실제로 인더스트리에서는 하도 인버터라는 용어를 픽스시켜 쓰다 보니까 그 앞단에 있는 렉티파이어가 스위치 모드 된 경우에는 스위치 모드 컨버터라는 얘기를 많이 씁니다. 그래서 이러한 거이기 때문에 좀 헷갈리시 마시기 바랍니다. 그리고 뭐 DC-DC 컨버터라고도 하죠. DC-DC 컨버터. 네? 그다음에 또 한 가지로는 이거를 렉티파이어라고도 하는데 기존에 다이오드 렉티파이어하고 차이를 둬가지고 다이오드 렉티파이어는 수동적이다, 패시브하다 그래서 이거를 우리는 액티브 렉티파이어라고 합니다. 능동적이다. 네? 우리 저기 전자회로에서도 뭔가 스위치를 써서 다이오드, 트랜지스터를 써가지고 필터를 꾸미면 액티브 필터라고 그러죠. 네? 마찬가지로 우리가 컨트롤할 수 있는 스위치를 써서 렉티파이 한다고 그래가지고 액티브 렉티파이어라고도 합니다. So what's the advantage of this system is the first one is now it can control the DC link voltage. Okay? So this can also vary the DC link voltage. So we don't see this degradation of output voltage with respect to output current, right? Do you remember? In diode rectifier, if this is ID and this is VD, we have seen that the VD is now decreased due to this effective internal impedance. And this impedance is due to current commutation, right? And this was seen as one of the disadvantage. But in this case, since we have a controllable technique, we can keep this DC link voltage quite flat. And also it can change the DC link voltage. That's the one advantage. And the other advantage is now the AC side current. Do you remember for the diode rectifier? For the diode rectifier, how did the AC current look like? It looked like this. If we have a constant current source at the DC link side, and how much was THD? Is almost 50%. So it's by far higher than the regulation limit of the IEEE 519. But when we are using switch mode converter, and this AC current is now very, very sinusoidal with a high frequency component, right? This is for switch mode converter. I'm now talking about the AC current. Okay? And this is diode rectifier. Okay? So THD can be maintained below the limit. So around 5% or 4%. So it complies with IEEE 519. So this switch mode converter has a lot of advantages compared to diode rectifier. But it has one disadvantage. What is that? Always. Better function comes with the price. It is more expensive than diode rectifier. Why? Because we have a lot of controllable switches. Do you follow me? Switch mode converter employs active switch, so it's more complicated. So complicated means it needs more electronic parts. So this becomes more expensive than diode rectifier. So this black one is the AC side current of diode rectifier, and the red one is AC side current of switch mode converter. Why it has some ripples? Because of high frequency switching. High frequency switching. So, and I just show as a one block diagram, but what about the inside? Fortunately, this switch mode converter and inverter are exactly the same in terms of the topology. So once you fully understand about switch mode inverter, then you are able to understand this switch mode converter. Okay? So starting from today, we are going to cover switch mode inverter, but you can also know about switch mode converter. So after finishing this chapter now, you are able to know everything about the motor drive, at least the power electronic side. Okay? So now let's march on to topology synthesis. So please think about what we have done in DC-DC converter. What was the first thing we have to do, or we have done in DC-DC converter part? We developed the theory from SPDT, right? Ideal switch. So using ideal switch, we were able to construct the topology. So we will follow the exactly same step. So we start with the SPDT and study or synthesize the topology. 자, 어떻게부터 시작을 하냐? DC-DC 컨버터 했을 때하고 유사합니다. DC-DC 컨버터 했을 때 우리가 어떻게 했냐면 SPDT, 아이디어 스위치를 통해 가지고 이제 회로 구조를 만들었죠. 회로 구조를 만든 다음에 회로 토폴로지를 공부하고 그 다음에 필터를 붙여서 회로를 완성을 했습니다. 똑같은 과정을 여기서도 거치겠습니다. What is our goal? What is our goal? Our goal is to synthesize switch-mode inverter. And what is inverter? It's a converting from DC to AC. So with somehow this side, we should have DC, right? And somehow this part, we should have AC. Okay? And I told you at the beginning of this semester that we should also define voltage or current, because DC can either mean voltage or the current. So we have to specify whether this is voltage or current. So now let me tell you that this means DC voltage. Okay. And this is AC current. So we have to connect DC voltage and we have to connect AC current. Now let me check your memory about SPDT. What type of sources, we have to connect now sources, voltage source or current source, right? We have to connect voltage source or current source. To which side? Now, what about the pole? What kind of source should we connect? Group 4. What type of source should we connect to the pole? Group 4. 전류원. Yeah, that's correct. We have to connect current source. So as I said, AC, we should connect AC current source. So like this. Let me use okay. Okay. We attach AC current source. Now, and everybody can remember that we have to connect DC voltage source. And if you remember this DC-DC converter, we connect like this. VDC1. Right? Oh, sorry. Let's say this is V throw 1, V throw 2. Okay? And this was IP, pole current. So This particular connection was what you have studied in DC-DC converter. Okay, you applied some DC voltage source and DC voltage source. Now, what about this, the pole voltage? This VP, pole voltage. This VP voltage now can take either V throw 1 and V throw 2, right? Okay, so if I draw VP, then depending on the switching state, the VP will take either V throw 1 or V throw 2, right? So this, and what type of voltage is this? Is this AC or DC? Actually, this is a DC with some AC ripples on it, but in terms of inversion, this is referred to as DC, right? This is not AC. We change from DC to DC. So in step-down converter, we assume this V throw 2 as a 0, right? That's how we create the topology of the step-down converter. So 여러분 기억하실지 모르겠는데 이런 구조를 해가지고 우리가 VTH2를 0으로 했을 때 그 스텝다운 컨버터 그때 우리가 했었지 않습니까? 이게 0이라는 얘기는 이렇게 연결한다는 얘기니까. 그래서 그게 이제 V throw 1하고 0을 이제 왔다 갔다 하면서 그 CBU를 조정해서 우리가 뭐죠? 출력 전압에 제어를 했었죠, 크기를. 자, 근데 지금 우리가 얘기하고자 하는 건 뭐냐? AC 전압을 얻고자 하는 거예요, AC 전압. 어떻게 해야 될까요? 어떻게 해야지 우리가 요 네거티브로 확 가는 전압을 만들 수 있을까요? 간단하죠? 이거 네거티브 전압 걸어주면 되죠? 네? 바로 V throw 2를 네거티브인 전압을 걸어주는 거예요. Right? So now if we have the same voltage, V throw 1, V throw 2, now this will go to the negative side. Okay? Now this becomes throw 2 voltage, negative. So VP will now oscillating between positive and negative. So now VP becomes AC voltage. 그죠? 이렇게 하니까 간단하게 VP가 AC 전압이 돼버린 겁니다. AC 전압이. 물론 이 파형은 구형파기 때문에 그 하모닉이 많은 H겠죠. 펀더멘탈은 사인파지만 그 외에 좀 하모닉이 있겠죠. 자, 그러면 요 구조를 보게 되면 일단 요거를 2분의 VDC라고 해봅시다. 뭐 같은 전압이면 좋겠죠? 부호가 반대고 같은 전압이고. 그럼 요거를 보면 여기 전압하고 여기 전압하고 좀 같죠? Right? These two points have the same potential as the ground, so we can connect this. So let me simplify this circuit. If I connect this, then it becomes like this. Okay? Still the same. Still the same. Now, how about this? This is VDC. So this VDC is exactly the same as the DC link voltage of the block diagram. 이거 아까 제가 얘기했던 DC link 전압 VDC하고 똑같습니다. 네? 똑같죠? 그래서 이렇게 연결을 하면 되는 거죠. 이 전압과 이거를 이렇게 연결하면 바로 인버터가 완성이 됩니다. Right? Now we completed this inverter structure. So this is half the VDC and this is half the VDC, so that this becomes like symmetry, right? 그죠? 대칭이 되죠? Symmetry. So people might have some questions like, oh, professor, how come do we have two different sources connected in series? Actually, voltage source can be modeled from capacitor, right? Capacitor. So actually, this side we can further realize by capacitor like this. Okay? 제가 지웠다 고치는 건 쉬운데 여러분들은 힘들죠? I'm sorry about that. Okay? And of course, now we can add here. Now, Diode Rectifier or Switch-mode Converter. Okay? Now this is the one simple structure of motor drive system for single phase. Now this is single phase. If we consider three phase, now we have to have three single pole double throw switch, but that I will explain later. Okay? So, pretty simple, right? Now you know about the inverter. 쉽죠, 여러분? 네? 이거 얼마나 쉽습니까, 여러분? SPDT 스위치에서 입력만 AC만 하나만 싹 바꿔주면 되는 거예요. 그죠? 입력 DC만 이렇게 부호만 딱 바꿔주면 출력 폴 볼티지는 스위칭 스테이트에 따라가지고 위로, 스로우 1으로 붙으면 위의 전압, 스로우 2로 붙으면 밑에 전압이 되는 거예요. 그죠? So now we have covered the basic structure of this inverter. So same as DC-DC converter, now we practically replace this SPDT with a realistic switch combination. 그러니까 저희가 DC-DC 컨버터에서 이거를 이렇게 꾸몄다가 얘를 다이오드와 스위치 페어로 바꿨죠. 마찬가지로 저희도 이거를 실제로 사용되고 있는 스위치와 다이오드 페어로 바꿀 겁니다. Okay, so now we will talk about that combination structure next class. Okay, so now I hope that you become familiar with this inverter starting from this SPDT solution. Okay, thank you very much. Bye.